morning. So, this is the last lecture on Kalman filters. So, we have seen most of the mathematical derivations and mathematical properties that major mathematical properties that the Kalman filter has. So, today it is an algorithm. So, to get the feel of the algorithm, some feel you can get from by analysis, but for algorithms you get a lot of feel by simulation. So, in fact, that is why the assignment was given in the last tutorial class. Those of you who are absent should take note of it. So, today we will show some limited simulation studies of the Kalman filter, mainly to substantiate what I have been always telling you, that it works very well. It removes a lot of noise. And we will also see the effects of some variations in the, there are some key parameters. So, if you choose them in various ways, what is the effect on the filter estimate, that is something that will be revealed through these simulations. Then we are going to touch upon certain other things. We do not have, I do not think we can treat them in any depth. So, rather than describing them in detail, more like we will talk about that such problems do exist. So, beware, and there are a number of references, you can always look them up. So, we are going to look at real computational issues, and so some of the things that could give problems if you really want to apply a Kalman filter in an actual case. So, they will be mentioned, and at least one variant of the Kalman filter which is very popular, known as the extended Kalman filter. There are even other variants of the Kalman filter. So, we'll have time to discuss only one variant, that is the extended Kalman filter, in some detail, and that will close our course module on state estimation. So, to begin with the case study, the system is the, as if there is a moving object, okay. It could be airborne, it could be waterborne, whatever, but it is moving. So, our objective is that we are assuming that, if we assume that there is some sensor which can get its position information, then can we extract, let us say, other information like its velocity. In some cases you may be also interested in measuring its acceleration. Now, it may appear to you that what is there, if you have position, if you differentiate position, you will get velocity, there is no problem. But it turns out that if you take such a naive approach, you land nowhere, you will get absolutely no estimate of velocity at all if you get a noisy measurement of position, and if you try to directly differentiate it. So what you need to do is, you need to do more sophisticated estimation, which is by Kalman filter, and we'll when we see our numerical simulation, this will be borne out. So, here we are assuming there are various kinds of models which are used. We are using a simple model where we have not exactly a constant velocity, but more or less constant velocity target with small velocity variations. We are assuming that the velocity is more or less constant, but there is a small acceleration component which is random and which is causing a slight velocity variation. So, the velocity is nearly constant, but then varying in a random manner. So, if we try to model the kinematics of such a system, then we can define as state the position and the velocity. Okay. So, xi and xi dot. Then we can write this state space equation. This is in continuous time, that is x dot, which is xi dot and xi double dot, is equal to ax plus bu. So, xi dot is equal to xi dot, therefore, this is 1, and xi double dot is that random acceleration component, right. So, this is my A matrix, this is my B matrix in continuous time. We can always discretize this. If you discretize, this matrix is nothing but e to the power at, where A is this. You can take, it turns out that for this matrix a square is 0. From a square onwards, a square, a cube, all higher terms are 0. So in this case, e to the power at is nothing but I plus a into t. So you get this, right. So this is the discrete time state matrix, and similarly if you take this, how do you get the discrete time input? That is by e to the power integral 0 to t e to the power a t minus tau b u tau d tau, tau between t to t plus 1, right. The effect of on xi dot will be the total accumulated effect of w from t plus kt to t plus k plus 1 t. That total accumulated effect you are approximating by a constant signal, as if at the kth instant you applied a constant signal Vk which remained constant from k to k plus 1 and produced the exactly same sampled value of this xi dot k plus 1, right. That is how you get it, right. This is a sort of this is what is known as a step invariant approximation of continuous time systems to get a discrete time signal, I mean a discrete time model. So this is your discrete time model. Now you have to estimate what is q. You have to now get the discrete time estimate of q, that is the process noise, because this process noise is not this process noise. So if you have a continuous time process noise, the discrete time process noise is actually related to the continuous time process noise by this matrix. This is simply just take, we have already found this. So if you, so this will turn out to be this, that is simple. So if you know the continuous time signal covariance, this will be the discrete time signal covariance, so that they will be related by various functions of the sampling time, right. So this is my model, okay. What is my measurement model? Measurement model is simple. Measurement model is simply 1 0 into x, because I am getting sampled measurements of the position, that is what I am assuming. So my C matrix is 1 0. Now is this system observable? It is. What is C? C is 1 0. What is CA? What is CA? Hmm? 0 1. So the matrix CCA is 1 0 and 0 1, it has full rank, therefore it is observable. Now which means that if indeed if you are given the position, then you can estimate the velocity correctly, but if your measurement was the velocity, for example if your C matrix is not 1 0 but 0 1, then what is CA? If your C matrix was 0 1, which means that you are measuring velocity, it was 0 0. So then the CCA matrix would have been 0 1 0 0. So it would not have been full rank. So if you measure velocity, your system is not observable. Why? Because from velocity you can never get position. Why? Because you need the initial condition. Even if you integrate velocity, unless you know the initial condition, you cannot estimate the position. So with respect to velocity measurements, this system is not observable, but with respect to position measurement it is, okay. So now this is sometimes called a second order model for obvious reasons, because the matrix has dimension 2. Sometimes it is called a constant velocity model, right, where you have a random acceleration input. Sometimes you can assume otherwise. You can assume that it is a constant acceleration model also, in which case your state dimension will become 3. Then you will assume that you have a small random jerk input. Jerk is the derivative of acceleration. So you could have, people use such models also, especially for tracking various kinds of targets which may be suddenly trying to speed up, again slow down in in a random fashion, sometimes it is useful to use the jerk model or the constant acceleration model, I mean a 3-dimensional third order model. So, we are going to have this case study incidentally, which was, I mean I am thankful to Shaboni for providing me with all these results. So, she has already done her assignment, if you note. The assignment was that was given is solved by her, and I am showing the results. So, you have to solve them yourself. So, we are going to show a kinematic state estimation case for a constant velocity model, and we will show typically what we want to show is how you get an SNR improvement. We had done a problem on that in our tutorial class. So, now we will see that actually what amount of SNR improvement takes place. We will also, we had seen some of the asymptotic steady state properties. I mean what does the state covariance matrix become? So, we will see that even if we do an actual simulation, it does tend to that value, it comes very close to that. So, our analytical values or expressions will be validated, and we will also see effect of uncertainty in Q and R, and we will try to provide intuitive interpretations of why the filter behaves that way, right. So, now we go to the computer and see our case study. So, we are here and we see this, is it coming? That is good. So, here so we are showing this one numerical simulation of a Kalman filter. What are the simulation conditions? The state model is a second order kinematic model, just the one that we have seen. The measurement is position only, assumed to be in Cartesian coordinates, that is incidentally this simulation is in one coordinate only, that is we are looking at the motion only in one coordinate. There may be two other coordinates which we are not looking at. The sampling time is 0.1 second. The number of samples for which these simulations were done was 1000, and these are the initial states: position 0 meter and velocity 10 meters per second. So, you can see that it really cannot be an airborne target because the velocity is too small. It can perhaps be a waterborne target, or even any other moving target. So, now let us see the first result. Okay. So, the values, first note the value of Q and the value of R. So, typically uncertainty in position measurement is about 100 meters, and Q is if you want to know the typical level of variation in the acceleration input, that is the random input that we have taken, you have to take about the square root of that. So, it is about 0.03. Note the unit here, it is meter square per second to the power 4 because it is square, right. So, the actual unit is meter per second square for the acceleration. Now, look at this. I mean we have deliberately done this, that is we have mixed a lot of noise. What is the scale here? If you can see 200, 400, 600. While you can see the amount of noise, measurement noise, that we have deliberately put in a 200 meter position, we have put in 100 meters of noise, right. So, huge noise, and can you distinguish between the estimate and the true trajectory? Hardly. So, the estimate is producing nearly the true trajectory, rejecting all the noise. So, such high noise is in position, right. And look at the velocity estimate, which is here. The scale is this point is, can you see the cursor? So, this point is 9.5, this point is 10, this point is 10.5. So, you can see the velocity estimate, it is varying between 9.5 and 10.5. Actually, it is varying less. This is an extreme case. Actually, what has happened is that here, I mean full convergence has not taken place, but actually it is probably varying between 9.75 and 10.25. So, that is the kind of error you are having in estimate. Can you imagine what would have happened if you try to differentiate this position signal? you would have been completely away. I mean, you wouldn't have got any signal at all. It would have been totally noise. If you differentiate this signal, this position measurement directly, where is the cursor? So you can understand what would have happened to your velocity. Okay. Now let's look at, sometimes the cursor is vanishing because this computer is slow. Now here, just to show the asymptotic results, we have plotted the diagonal elements of P, that is with estimation between 0 and 1000 points. You can see that as these state estimates become better and better, the state error covariance sharply falls and then reaches a steady value. So the P matrix indeed converges. This is an observable system, right? Controllable as well. And and the convergence is, note the convergence, about 300 to 400 it has mostly converged. It has come to about 90-95% of the steady state value, right? So this is important, because in some other cases, as you shall see, the convergence will become significantly slower, and for good reason, right? So the filter, the convergence means that how sure the filter is becoming about the signal properties. So when the filter converges, it has become, whatever doubt it had, it also kind of learns. So at some point of time, it has learned whatever was there to learn in the data. It cannot reduce uncertainty beyond that. So the faster the convergence, the faster the filter learns. Okay. So look at the convergence. Look at these figures, right? If you solve the Riccati equation, actually P equal to psi p, you will get these values 25.18 like that, while here it has come to 40.5, same scale of things. And one experiment which we did not do is that this value is actually independent of the value of P0 that you choose. You could have started with a 10 times high P0, it will still come to this value, right? And look at the velocity. Riccati equation says 0.008, we have got 0.0154. So roughly about 1.6 times. I mean, if you really had run it for another 2000 samples, probably it would come to 0.008. All right. So now let's see the next one. So this is my standard case where the value used in simulation has been used in the filter. So as if the filter knows the true Q and the true R of the data, right? Now next plot. What have we done here? See what we have done here. What we have done here is that we have still used the same data, but now we have told the filter a wrong Q. We have told the filter a much higher value of Q. There is no guarantee that you will know the exact value of Q which is there in the data. You have to make an estimate. So what happens if you make a grossly wrong estimate? Okay, this is 1000 times Q. So which means that you are about 30 times off in your estimate of the acceleration levels that are coming. See the measurement data is not that different. Can you see that? The measurement data looks almost like the previous data. Why? Because the measurement data is position, so acceleration gets 2 times integrated. So every time you integrate, you are actually basically putting a 1 by omega gain. So power is sharply falling. So the effect of that much high increase this thing on the acceleration level, true acceleration is, it's not that high, because after all signals are zero mean. So when you doubly integrate, signals do not, the position signal is not that much affected, but and the measurement noise is at the same level, right? So therefore the position data looks nearly similar, very similar. But look at this estimate now. Previously remember that we were between 9.75 and about 10.25. Now we are, this is 9, this is 9, this is 11, so it is almost reaching 12. because the filter assumes that the velocity should vary much, because it has been told that the covariance of the process of the acceleration is 1. So if the covariance of the acceleration was really 1, then it would have a large velocity variation naturally. So it is interpreting the data in that light. Therefore, the estimate that it is producing, this cursor is vanishing from every now and then. So you get a much more varying estimate. Convergence is roughly the same, but the steady state values have increased significantly, because the filter assumes that it cannot reduce. If the data has so much high Q, then velocity and position, you see the Riccati equation values are significantly increased. It was 40, now it has become 142. This was 0.008, it has become 1.41. Convergence is pretty fast, so it has nearly converged to the steady state values. Now let us see the next one. In the next case, what we have done is Q we have maintained and R we have increased by 10 times, not 10 times actually, 100 times. So now my measurement uncertainty is of the order of 1000 meters, huge. Actually not in the data, I have told the filter that the measurement uncertainty is this much. I have given a wrong R value to the filter. So what is happening? Data is same, because data is generated by that. Now you see, first of all look at this. Here you will probably assume that the mean of the estimate is not matching. Now that is not the case actually, that is happening because this is a plot between time instance 300 to 500. Now so now look at this convergence pattern. Why is this mouse stopped? Now look at the convergence pattern. Now the convergence pattern has become much slower. The filter does not converge. Why? Because the filter is now, because it knows that there is so much error in measurements. See, the filter, the filter works on two things. It works on the knowledge that you have given it, values of Q, R, A, B, etc., and the signal it is getting. These are the two things based on which it makes the estimate. Now this time you are telling it ABR etc. This time you are telling it that the signal that you are getting is highly uncertain. For the same motion, if you perform a second experiment, you can get a totally different signal. That is what you have told the filter, because R is so high. So the filter is now much more cautious. It does not want to come to a hasty decision, right, because it knows that there is a lot of uncertainty in the data. So it takes time to converge. So the moment you increase R, filter will reduce its gain and will start converging slowly. In fact, this has happened because this estimate is not yet converged. Actually at 300 this is far from converged, right. So therefore this is not a, I mean you cannot really expect a zero mean. I mean the filter is still coming down. I mean especially the effects of P0 etc. are still getting reduced. And now interestingly, look at these Riccati equation values. See, the position uncertainty steady state has become from, previously it was 40, then it became 140, now it is 800. While the velocity estimate has not changed. It is still, it was 0.008 in the total ideal case, now it is 0.02. Why? Because the Q is the same. See, velocity is not affected by R, velocity is directly, position is affected by R. So therefore the steady state variance of velocity is not that high, it has not increased. Previously when you gave it a wrong value of q, it immediately increased the covariance of the velocity, because q directly affects velocity, right. And then we will see the last result. So this is the case. Then let us see the next one, the last one. Here very interesting thing, that what happens if your noise is colored, that is measurement noise is actually not white, it is colored, and the filter bandwidth is well within the system bandwidth, and now in that case what will happen? What will happen is that the filter tries to explain noise. You know, it finds that if the noise bandwidth is largely contained in the system bandwidth, then part of the noise can be explained by the system behavior. See, if noise is white, then and if the system bandwidth is very low, then you cannot really, no input to the system can really generate that noise, because the noise is white, much of its power lies well outside the bandwidth of the system. So the system, whatever input you give, it can never generate that sequence which you have measured. But if your noise bandwidth is low, suppose system is also 0 to 2 hertz, noise is also 0 to 2 hertz, then the system can explain a lot of noise, because there will exist inputs which can produce sequences which are very close to the noisy sequence, because their bandwidths are same. So what you are doing now is that you are actually by colored, basically you generate white measurement noise and then you pass it through a low pass filter. So the colored measurement noise bandwidth is largely within the system bandwidth. So now the system starts explaining noise, that is the estimate will try to eat up, will try to include the effect of noise. See, this scale is significantly higher, again the cursor is gone, this scale is significantly higher, this is 0, this is minus 1000 and the top one is plus 1000, previously it was 200, 400, 600. So the scale is much higher, still this estimate is now, see, whenever the average value of noise is going up, it is going positive, whenever it will go down, it will go negative. See, here the average value of noise is significantly positive, can you see that, the green lines? If you take an average within that interval, it will become significantly positive and the estimate is going up, right. Plus there is correlation. So the estimate is, you know, trying to track the noise DC, I mean low frequency components. So if you, this is why you should add, in this case you should actually add the noise states also to the Kalman filter, extend the states and then reformulate the problem such that the noise states will also be estimated, then your actual system state estimation will become white and flat again, okay. So again, you know, convergence is still slow because our R is still very high. So this is what I wanted to show about Kalman filter. You can yourself do many experiments with your own code and see better things. So we come back to our notes. Now just very briefly I wanted to discuss that if you really want to make a numerical implementation of a Kalman filter, then there can be several problems, and there are several solutions. One very normally people very highly recommended implementation of the Kalman filter is what is known as the square root filter. So we will just see what is the philosophy of the square root filter, nothing else. So among the possible problems of, you know, not getting filter performance is modeling error. If your ABCD matrices are not correct, then your estimate will degrade. Sometimes it can even be sometimes it can even diverge, especially if the dynamics is unstable and if you start having modeling errors. Similarly, obviously this is also a kind of basically error in the input that you are given QR P0. We have seen what happens if you have errors in QR and P0. Filter will become slower unnecessarily, right. So this shows that incidentally in our kinematic model, at least there was no chance of having a modeling error, because after all velocity is after all the integration of acceleration. That for that you don't need to model anything, it's already modeled. But in other cases, if you want good estimates, you should spend time. See, remember that algorithms can never replace experimentation in engineering. Experimentation always has a very distinct role. So don't think that just by having a Kalman filter you can sit in a nice air conditioned room and get fantastic estimates. That is not going to happen. You have to go out there in the field, measure things, model them, get data, then only you will get good estimates sitting with a computer, otherwise not. So there is need for consider very good modeling and measurement, estimation of QR and P0 if you want to get good things. Sometimes what happens is that these two things together. See, if you remember, the Kalman filter has a term called CP transpose plus R inverse. So wherever you have inverse, there is caution. Is it invertible? So sometimes suddenly you are running the filter and suddenly it should, if it at some point it becomes numerically singular, the estimate will explode, right. And just imagine that you are in mid air, flying some object which constantly works on your target, and then in mid air your Kalman filter has become singular. What a situation to be in, right. So this can become singular. Why? If the conditions of these deteriorate. So if R is nearly singular, or if CPC transpose is singular. Now CPC transpose will be singular typically when C is, it will definitely be singular if C does not have full row rank. That is, all the rows of C are not independent. Maybe using, so which means that you are using a third measurement which is really redundant, because the third measurement you can always generate by taking suitable sums of the other two measurements. In that case you should delete the third measurement, not use it, because this might lead to singularities. So these two can give you numerical problems of non-invertibility of matrices, right. There are several solutions, that is, check, sometimes add a constant non-singular matrix, like that. Sometimes there you may get outliers. Outliers means that you have generally observed that Q and R are, xi and eta are random, they have a certain kinds of Q and R, but sometimes you get, for some reason, sometimes you get some isolated data points which are suddenly will give you a peaky disturbance, glint kind of things. So if you are not aware of those, and if you don't handle them, tackle them, whether first of all see whether you are having such samples. If you have such samples, it is better not to update based on those samples, because they do not really belong from the probability distribution which you have assumed for the filter. They are very sporadic signals which actually belongs to a totally different probability distribution. So if you update based on these outliers, what will happen? Your estimates will suddenly get a big shock. You are arriving at close to the true estimate, suddenly one data point comes and it shakes your estimate up, because the Kalman filter suddenly finds a very bad data point and it will considerably change its estimate. So these things should be handled. Then there are sometimes numerical problems can come due to various reasons. One reason is that, another reason is due to scaling problem, basically due to rounding and truncation errors, and that can happen if you have variables for example, which are say one variable is of let us say 1000 meters, that kind of values. Another variable is I mean basically various components of the state. Another component is 0.001 millimeter per second square. So if you have such things, then you can imagine that if you take their covariances, the P matrix, some element will be 10 to the power 8, some element will be 0.1. So if you want to manipulate such matrices, due to numerical precision, your calculations will be significantly away from the ideal calculations. I mean, this itself by itself is a science and requires very complicated analysis to actually find out why it happens, when it happens, how to avoid it. But this can give you considerable problem relating to leading to divergence, especially the P matrix is supposed to be at each stage of computation of the Kalman filter, the P matrix is supposed to be symmetric and positive definite. It can very well happen that C is either not symmetric or not positive definite because of these cases. If the C matrix is not symmetric or not positive definite, your estimates will go astray. See, the health of the P matrix is of critical importance in actual implementations of Kalman filters. So there is one algorithm which is widely used, which by itself ensures that the P matrix is always symmetric and positive definite, whatever the precision. It is built in the algorithm, and that is called square root filtering. So the whole idea is that don't update P. In the Kalman filter we update P, but don't update P, but rather update the square root of P. By the square root of P I mean such a matrix such that P into P to the power half, that is what I call the square root of P, P to the power half into P to the power half P, whenever I need P I actually calculate it out of this, but I update this. So you see, by construction it is symmetric and positive definite, it cannot be otherwise. It cannot become otherwise due to updating, because I am updating this and then whenever I am needing P I am just multiplying a matrix by its transpose. So it must be positive definite, must be symmetric, because whatever truncation will take place equally in the symmetric elements. So the matrix will remain symmetric. And then you can actually the square root of this is not uniquely defined, so you can choose one LDL transpose factorization or some other factorization, QR, various kinds of things. So the whole approach is that you first factorize P0, that is compute P0, factorize it into P0 to the power half and P0 to the power half transpose, and then go on have update laws which do not update. You have to compute Pk plus 1 given k, rather than doing that update its square root. Similarly update the square root of Pk to the power k, and then once you have this square root of Pk given k, then you construct Pk given k and then you construct Kalman gain, because Kalman gain will require Pk given k. So while updating you update the square roots, then while calculating Kalman gain use it using this equation and then update state. So this avoids many this algorithm is now fairly stabilized, discovered by one, various people developed it, Bierman, Potter. So now it is very stable and well used implementation. To end, we want to just have a look at extended Kalman filtering for two reasons. Firstly, because a large number of estimation problems, especially in aerospace, often turns out to be non-linear, because of the fact that you see we obtain a very nice linear model because we assume that our measurement is in Cartesian coordinates. If our measurement was in polar coordinates, as happens often with radar, all our equations theta and r would have been non-linear differential equations, not linear. So how do you estimate state? That is, how do you estimate r and theta? So some good solutions are needed for, because this is a very common thing, that is estimating. one of the biggest applications of Kalman filter is in target tracking, especially in aerospace applications. So you see that there is a simple formulation available by which you can update, I mean do a Kalman filter like it is an approximate Kalman filtering for a linearized model of a nonlinear system. So at least you can do something. So we are assuming now that we have a nonlinear system given by like this. So this is now not a matrix but a vector function, nonlinear function. This is also a, so you see that the B matrix is now a function of x, so it itself is nonlinear. Similarly this is nonlinear, this is the measurement noise. So how do you linearize? The basic idea of linearization of any nonlinear system is to break it into a Taylor series approximation. I am sure you are familiar with linearization of nonlinear systems. So you break up this into its Taylor series, break up this into its Taylor series, f and g, and now you see what is happening. In this term is known. Can you see this? That is, this term is known. What we are doing is we are trying to linearize the actual model around my last estimate. So I have obtained an estimate x hat k given k at any point. True state is somewhere close, I do not know where. So I am trying to find out I am trying to find a linear approximation of the true state around my estimate. So normally you linearize around x naught u naught. So you linearize about an operating point. In this case the operating point is my estimate. So obviously I am assuming that my estimate is kind of good enough, and the true state indeed lies reasonably close. If it does not lie reasonably close, this approximation is not good. So I have kind of the intuit, it is like putting the cart before the horse, in a sense that while formulating the estimation algorithm, I am kind of assuming that it will give me a reasonably good estimate, and xk is going to be close to my x hat k. This is a chicken and egg problem which plagues this algorithm, and it is typically very difficult to prove its stability. So what I am doing is that now you see this is now known because my fk is a known function, maybe nonlinear but known. X hat k I have already computed. So this is a pre-computable thing. Similarly, this is a pre-computable thing. This is not known. This is known. This is del f k del x k. This is a functional form which is evaluated again at x hat k. So it is computable. Similarly, this is computable. This is computable. So these are all when you are standing at x hat k, these functions are all computable. So anything which is known is like a known input. So now I am redefining that let uk be is equal to this into this. So you see the known two terms, this term and this term, I am assuming to be a known input because they are computable. I know them beforehand. Similarly, if I know x hat k, then I know gamma k, this term. Similarly, if you define a new measurement, which is the measurement minus two known quantities, you can always define it as a new measurement because it is computable. This is your measurement, this is computable, this is computable. So you can always define a new measurement. So now once you have done that, you can write this equation in terms of these and it will become a linear Kalman filter. That is the whole idea. So the whole idea, so now if you write it in terms of this u and gamma and this is and this w, now it will become like the known Kalman filter, I mean linear Kalman filter. So this is like your matrix AK, this is xk, this is your known matrix uk, this is gamma k xi k is unknown, gamma k is known, and this is like ck. So in the vicinity of x hat k, the system dynamics behaves like this linear equation. So around x hat k, you can now, at least for one step, you can have a linear Kalman filter formulation of this. Then you will get a new x hat k plus 1, you will have to again linearize the system around that operating point, find these matrices again, new matrices, formulate a new Kalman filter around that operating point and do one more step update, like this you do. So every time you go, you find a new system and you find a new Kalman filter and you make a new update. So this is how you go when you have a nonlinear system, but at least locally for that update is optimal, right. So this is called extended Kalman filtering, and it works, it does work, a lot of people have used it, but it sometimes known to suffer from stability problems, mainly because of the fact that it's you are right in the beginning, you are sort of assuming that the estimate is close to the true state. So it will depend a lot on initialization. If you are starting your estimate very far away, then this approximate model is very bad. And if it is very bad, and if you make a one step update using your Kalman filter based on this model, it might take your estimate in wrong direction, because you are using a very bad model. So it has a Kalman, EKF has a kind of a locking problem. It sometimes cannot lock onto the estimate. Once it can lock on, it can go on, right. So sometimes you need good initializations for these kind of algorithms. But it can be it's actually a nice point to end our Kalman filtering discussion, because the EKF can be used, it has been used for simultaneous state and parameter estimation problems. You see, suppose you are given a system in which you have to estimate the state, but you do not know its model, or suppose this model keeps on changing. So then what do? So then you have to simultaneously estimate the state and the model parameters. So if you want to do that, and obviously model, for example, xk plus 1 is equal to ak xk is linear if ak is known, is completely non-linear if ak and xk are both unknowns, because you are having a product of two unknowns. So it is a non-linear model. So in such cases you can use the extended Kalman filter and write that let my states be xk plus 1 ak plus 1, then I write that this will be what, then how do I put ak plus 1, you can write as ak equal to ak, so this will probably be 1, and xk plus 1 will be what in this case, how can we make it ak xk, we can't make it ak xk, but theta probably we have to it is still non-linear, but then we have to, yes, this is a non-linear system, this will become the function fk, which is also a function of xk. So now we have to actually we cannot directly find a linear equation, obviously. It is a non-linear equation for which we have to now formulate the EKF, but this can be solved using EKF, and this is sometimes called adaptive state estimation, that is when you are trying to estimate the state when you do not know the system. So we will stop here, and incidentally we have because we have ended with a problem of parameter estimation, and in the next module we are that is going to be our subject. In that case we are not interested in state estimation, signals will be known, and we will be rather interested to estimate the system model. So that is system identification or system parameter estimation, which will be the next module and the subject of next 6 to 8 lectures. Just one line conclusion on Kalman filter: very effective and popular, wide usage for aerospace applications, many other applications, maybe also in Navy, mainly for strategic applications. Computationally it is not a very simple filter, that is why sometimes people use fully knowing that it is not optimal, even for target tracking, people use constant filters known as alpha beta filters or alpha beta gamma filters, which are time invariant filters, very simple to compute, does not give such good results. Incidentally, filtering is not the only problem that you can define. You can also define a prediction problem where you are getting measurements up to j, up to k, and you are interested in knowing the state at k plus 9, k plus 10 in future. That is called a prediction problem, which we only talked about one step prediction. You can do multi-step prediction, very effective in many situations, including chemical process control. Sometimes you may like to do smoothing. Sometimes you have the full measurement available, offline thing you are doing. You have all the data points available from 0 to 1000. So using 0 to 1000, you can try to estimate x200. So you are not only using past data, you are also using future data, because the application is offline, right? So such cases are called smoothing, where using data up to k, you are trying to estimate maybe x k minus 25, right? So there are also formulations of the Kalman filter type smoothing problems which we did not consider. And there are several variants of the Kalman filter. This is not the EKF is not the only one. There are filters called information filters, Chandrasekhar filters. There are filters called adaptive Kalman filters where Q and R are along with the state estimates, Q and R are continuously tuned. There are filters where you don't know what one kind of approximation of this will be that you have 3-4 Kalman filters tuned for 3-4 different Qs, and at any time use only one of them. So you have all the 4 filters running, and you sometimes switch from here to there, sometimes use this, sometimes use that. So you have what is known as an interactive multiple model Kalman filter. So these are typically used for various kinds of, especially for maneuvering targets. Okay, suppose the pilot, if you are trying to design a, let us say, guidance system for a missile for an aircraft. Now the pilot is not going to sit pretty, knowing that a missile is chasing it, because it will also detect. It's a cat and mouse game. So it will also know that a missile is chasing. So it will do maneuvering. It will turn right, left, up, go up, down, accelerate, decelerate, try to evade the missile. So from the point of view of the missile, you have a target whose acceleration level will be unknown and which will be suddenly changing. So if you want to estimate its targets, you have to use different filters. You can't get very good results by using the same filter with one Q. So for such situations, you sometimes use this interactive multiple model filters. So that's all for today. From the next class, we will start system identification. Thank you very much.